An energy source is a naturally occurring substance or process that allows human civilization to obtain the power required for life and production. For centuries, humanity has systematically mastered a succession of these energy carriers, progressing from firewood to coal and eventually to natural gas and crude oil. These conventional sources rely on a single core mechanism, the widespread combustion of fuel. This chemical process releases large volumes of carbon dioxide and other harmful compounds directly into the atmosphere. The steady atmospheric accumulation of these gases drives the greenhouse effect, trapping heat and accelerating the melting of the Earth's polar ice caps. This environmental reality has forced the scientific community to develop alternative energy sources. However, the theoretical potential of these renewables must be weighed against the rigid laws of physics that govern macrogrid integration. Attempting to dismantle the centralized power grid and replace it with autonomous, local microgrids without accounting for these physical boundaries is an engineering impossibility. This animation illustrates the mechanics of photovoltaic panels, devices that convert sunlight directly into electricity. Photons from the sun strike a semiconductor surface, displacing electrons to create a direct electrical current. Today, the global installed capacity of these panels exceeds 770 gigawatts, yet solar energy still accounts for only about 3% of global electricity production. The geographical footprint of solar infrastructure is expanding beyond early adopters like Europe, China, and the United States. Nations including Kazakhstan, Kenya, Saudi Arabia, and Egypt are investing heavily. In regions like South Korea and Chile, engineers are deploying novel floating photovoltaic systems directly on the surface of water bodies. These floating systems offer distinct advantages, namely improved cooling of the panels and reduced water evaporation. But when deployed on saltwater, they reveal a specific flaw. Salt residue from splashing water accumulates on the array, requiring constant cleaning. Surface contamination scales directly into systematic failure. A proposed mega-project to build massive solar farms across the Sahara Desert was abandoned because the constant coating of panels with blowing sand and dust, combined with extreme transmission distances, made the infrastructure unworkable. The history of solar capture extends back to ancient civilizations using lenses and mirrors to focus sunlight. By 1839, French physicist Edmond Becquerel recorded the generation of electric current in electrolytic cells exposed to light. This discovery became known as the photovoltaic effect, a physical process where light produces voltage in a material. In 1905, Albert Einstein provided the necessary theoretical foundation for this effect by introducing the concept of photons. Photons are discrete packets of light energy that behave as both waves and particles, establishing the mathematical basis for solar capture. The practical realization of Einstein's theory occurred in 1954 at Bell Laboratories, where scientists developed the first silicon photovoltaic cell. With an initial efficiency of 6%, these cells found their first large-scale application, powering early artificial satellites in the vacuum of space. Despite its silent emission-free operation, solar generation suffers from severe limitations. Output is inherently intermittent, dropping to zero when sunlight is unavailable. Furthermore, manufacturing the required panels necessitates extracting rare earth metals using toxic substances, complicating the technology's clean image. By its physical nature, wind is simply a transformed state of solar energy. Uneven solar heating of the Earth's surface creates localized pressure differentials. These variations force air masses to move, generating the kinetic energy we experience as wind. This schematic traces the complex electrical conversion required to harness that kinetic energy. A rotating turbine first produces alternating current at an unstable frequency. Alternating current is an electrical charge that periodically reverses direction. This raw power must be rectified into direct current and then inverted back into alternating current at a stable frequency, such as 50 Hz in European grids. The modern wind industry operates at an explosive scale. China leads global installed capacity, expanding an onshore complex in its northwest to a planned 20 gigawatts, while simultaneously developing a massive 40-gigawatt offshore installation along its coast. Humans have harnessed wind for millennia, from propelling vessels along the Nile to turning medieval grain mills. But the first documented use of wind for electricity occurred in late 19th century Britain, when inventor James Blyth built a turbine to power his property. His proposal to use the surplus energy to electrify the local town was rejected. Aerodynamic physics dictate that a 3-blade rotor is the optimal configuration. Fewer blades reduce the efficiency of energy capture, while adding more blades increases aerodynamic drag without providing a proportional benefit in power output. Wind power shares solar energy's flaw of intermittency, but adds a spatial constraint. Wind turbines generate low-frequency infrasonic vibrations. Infrasonic sound refers to acoustic waves with frequencies below the lower limit of human audibility, which can affect living organisms, necessitating isolation from residential zones. This visual demonstrates the continuous processes of moisture evaporation and air mass movement in the lower atmosphere. These interactions cause massive electrical charge separation. By winter, the electric field strength near the Earth's surface can escalate to 300 volts per meter, holding a potential of 10 million gigawatts. The scientific pursuit of harvesting this atmospheric voltage spans centuries. Early researchers deployed dangerous aerostats laced with metallic needles to collect charge, while pioneers like Nikola Tesla proposed systems to convert the high direct voltage of the atmosphere into usable alternating current. Modern theoretical models attempt to resolve this by deploying high-altitude collection probes. These tethers would draw electrical charge from atmospheric moisture droplets and store the power in massive supercapacitors. Supercapacitors are high-capacity energy storage devices that can accept and deliver charge exponentially faster than standard batteries. Extracting energy on this scale carries severe global risks. Removing massive quantities of electrical charge from the atmosphere could disrupt the Earth's global electrical circuit. This interference threatens to trigger unpredictable climatic shifts, intensifying thunderstorm activity in some regions while inducing droughts in others. Another experimental frontier is osmotic diffusion energy. This system harvests power at river estuaries, utilizing the pressure differential created when fresh water and saltwater mix across a semi-permeable membrane to drive a mechanical turbine. While these unconventional sources offer theoretical yields that dwarf human demand, their dependence on highly specific geographic boundaries and atmospheric conditions makes them unscalable as primary global energy solutions. The absolute limiting factor for all renewable energy is the lack of large-scale storage. Gravitational storage systems attempt to solve this by functioning as mechanical energy reservoirs rather than primary generators. This diagram shows the core mechanics. During periods of surplus grid generation, excess electricity powers motors to lift heavy masses, effectively storing potential energy. When the grid faces a deficit, that energy is released by lowering the masses, running the motors in reverse to generate power. This mechanical process is the physical equivalent of pumped storage hydroelectric plants, where water acts as the descending weight to smooth out the inherent variability of wind and solar output. An ideal global storage technology requires specific parameters: massive capacity, rapid charge and discharge rates, environmental compatibility, low cost, and total scalability. Until engineers solve this storage bottleneck, the explosive deployment of alternative energy remains physically impossible. Without a place to warehouse surplus power, the growth of renewable generation is limited by the real-time demands of the grid. The concept of distributed generation promises that individual households can act as autonomous nodes of energy production. Equipped with roof solar panels and backyard wind turbines, consumers theoretically generate their own power and feed any surplus back to the local network. History counters this decentralized vision. The evolution of electrical power proves that the laws of physics necessitate centralization to manage complex energy systems. Grid stability requires a dominant generating unit. A massive central node regulates the frequency at a steady rhythm. Other sources synchronize to this master wave. During a collapse, only this centralized generator has the inertia required to re-establish the baseline frequency and restore the system. A resilient energy network requires a hierarchy. Stripping away the central anchor removes the physical mechanism that allows synchronization to exist. Consider a hypothetical scenario: a village of 100 homes, 30 of which operate their own independent solar arrays, wind turbines, and biogas generators. Suddenly, the high-voltage substation fails, cutting the village off from the primary grid. This disconnection forces a critical engineering question. Without the centralized macrogrid's massive inertia, which of those 30 tiny local generators assumes the burden of setting the reference frequency for the isolated microgrid? Without a central conductor, the network frequency wildly fluctuates. Small local generators emit mismatched colliding wave frequencies, destabilizing the voltage. Detecting this chaos, local inverters trip their automatic protection relays in sequence to prevent hardware damage, shutting off power generation entirely. In this scenario, the autonomous microsystem breaks down into a collection of useless, isolated hardware. The physical difference lies in infrastructure. A high-voltage transmission network utilizes directional protection relays, automated power flow regulation, and centralized dispatch management. Transferring generation to the unmonitored, branched chaos of a local distribution network removes these essential control mechanisms. To sustain an isolated microgrid, you must install massive, localized battery storage, freight container-sized units. Deploying this industrial-scale infrastructure into residential zones is economically unviable. Distributed generation remains a highly effective technology, but strictly as a supplementary feed. It relies on the macrogrid's infinite buffering capacity to absorb variable output and maintain system frequency. Integrating every alternative source requires a rigid, multi-layered hierarchy. Power flows from heavy, high-voltage generation through regulated transmission lines, eventually reaching low-voltage local consumption with absolute stability. Genuine grid resilience does not come from dismantling the network to run on isolated microgenerators. It comes from accepting the physical limits of alternative energy sources and integrating their output into a master, centrally managed architecture.